So we've just finished figuring out how we might compute the integral of a function of two variables where the limits of integration on x and y are constants. Right? X equals -3 to 3, y equals -4 to 4. And we decided that the region of integration being described there, if x is allowed to range between those two constant bounds and y is allowed to range between those two constant bounds, what we're really describing is a region in the xy plane which is rectangular, right? And whenever my bounds, my limits of integration on an iterated double integral are constants, I must be describing a rectangular region. And rectangles are great, but we might want the flexibility to be able to describe regions that are not just rectangles, right? If I take a look at the volume that we computed and I look at it from above, there's my rectangle, right? That's what it means to let x and y just take on those constant bounds from -3 to 3 and -4 to 4. So what if we want to do better? Like, what if we want to use regions of integration in the xy plane that are not rectangles, but maybe are bounded in some other ways? Like maybe this nasty blue-looking region is the region of integration that I want to consider. What kinds of limits of integration would we want to have in order to describe this wacky thing? So that's what this section is about, is giving us the flexibility to be able to describe general regions in the xy plane by writing down inequalities on the variables x and y, and doing so in a very particular way that is going to make iterated integrals possible and sensible in the process. So the preview activity in this section on double integrals over general regions is asking us to think about, and then actually do, I suppose, what it would look like to take an iterated integral, or to set up a double integral that could compute the volume of a tetrahedron. So here's a tetrahedron in the first octant of xyz space that is bounded by the origin, and the other points are the points I, j, and k. So 1, 0, 0, 0, 1, 0, and 0, 0, 1. So those vectors are called a, b, and c here. They define this tetrahedron. And then they're setting up for us a geometric way to compute the volume of that tetrahedron. And that geometric way is just to use the scalar triple product, which computes the volume of the parallelepiped that is defined by those three vectors, and then dividing that volume by 6 to get the volume of the tetrahedron that's there instead. And so that's part A, and I've done part A for you so that we can get straight to the good stuff of integration. So for this, what we want to do is think about how we might describe this tetrahedron as the volume underneath the graph of some function of two variables. And by doing so, figure out what region in the xy plane we would need to make our region of integration. So the region in the xy plane that becomes the region of integration is this triangle that's marked here with vertices at 1, 0 and 0, 1 and the origin. And then this problem is going to walk us through the process of finding inequalities that describe x and y that give us exactly this shape, and that could then let us find the volume of this tetrahedron using a double integral instead. So if the top surface of this tetrahedron is described by the graph of the function 1 minus the quantity x plus y, then our job is going to be to figure out what limits of integration on x and y will describe for me what we would call the projection of this tetrahedron down onto the xy plane. So we just squish the tetrahedron down on the xy plane. It looks like this triangle. And so by finding inequalities on x and y, let's see if we can describe this triangle and do part B to get this preview activity started. If our job is to describe this triangle in the xy plane, then what we end up wanting to do is find a pair of functions, y equals f of x and y equals g of x, that describe for me kind of the bottom face of my region as well as the uppermost in the y sense face, right? So if I take a vertical slice, a vertical cross section of this, then the bottom edge of that cross section is going to be on the graph y equals 0, and the top edge is going to be on the graph y equals 1 minus x. Right? And so that is where the first one of the inequalities in this problem come from, right? Y ranges between 0 and 1 minus x. And then once I've decided what y should be ranging in between, then I just need to figure out what x ought to range in between. And here's where sometimes people get twisted around. They decided when they wrote up this activity, that just letting x range from 0 to 1 without making it a function of y is going to be enough. And one of the reasons I think we can think about that, and you alluded to this in your write-up, you said that the triangle's base is ranging from x equals 0 to x equals 1. And that's right. It's like what we're doing is taking this triangle and squishing it down onto the x-axis and looking at just the shadow of the triangle on the x-axis. And that shadow goes as far to the left as x equals 0 and as far to the right as x equals 1. What sometimes people will do if they're getting mixed up in the process is they try to do x ranging from, they take this equation, y equals 1 minus x, and they solve it for x in terms of y, so x equals 1 minus y, and then they say, let's let x go from 0 to 1 minus y, and y goes from 0 to 1 minus x. But that creates like a circular definition problem. We'll also see that that becomes a problem in iterated integrals later on, because our iterated integrals need to be giving us one fewer variable each time that we do an integration step. And so the number of variables in our limits of integration should also be going down by at least one each step as we go from the inside to the outside. So this is what I call the tape measure method for describing a region in the xy plane. We know what region we want, and then we take some cross sections of it. So we try to find a function that bounds either the bottom side and the top side, as we did here, or potentially the left side and the right side if we wanted to let x be function of y instead. That's something we're going to talk about a little later in this section. And then once we know what functions are going to bound the bottom and the top side, then I squash out the y variable and I look just on the x-axis at how much of the x-axis do I need to describe this region. And it's that squashing step that is probably the most important step in the process. Otherwise, you're going to get sort of nonsensical results coming out the other side. So in this example, our triangle is described by the inequality y ranges from 0 to 1 minus x, and x ranges from 0 to 1. So in part C, they ask you to carry out the definite integral of the function 1 minus the quantity x plus y over the iterated integral whose bounds are y ranging from 0 to 1 minus x and x ranging from 0 to 1. And so this is your chance to get some practice doing one of these iterated integrals from the inside out. It's just that now the limits of integration on y involve x. Right? So we're going to have an x in my limit of integration here. But then that's okay from the point of view of the inner integral, because in the inner integral we're thinking of x as though it's a constant. Right? And so it's okay if I have an x as part of my limits of integration. It doesn't create a problem with the definition of definite integral because we're treating x as though it's a constant in that process. So take a minute and work through the iterated integral in part C that comes from setting up the limits of integration according to how you've described this triangle. So, well, of course, one of the challenges with integrals is that they just take a while to compute sometimes. So with the short time that we have today, just to walk through the evaluation of this iterated integral, right? We take the antiderivative of 1 minus the quantity x plus y as a function of y, treating x as though it's a constant. And it's that treating x like it's a constant that lets us have an x participate in one of the limits of integration, right? The top limit, y equals 1 minus x. So the antiderivative, which we can make into y minus xy minus half y squared. I evaluate that at y equals 1 minus x. So I plug in a 1 minus x for y in my upper limit. And then I plug in a 0 for y in my lower limit. When I plug in the 0, everything vanishes. And so I just get the value that I get when I plug in 1 minus x, which is 1 minus x times 1 minus x minus half of 1 minus x squared. And so I get half of 1 minus x squared as the value of my inner integral. And then, because the limits of integration on that integral are constants, and the outermost integral in an iterated integral will always have constant bounds, because after we do it, we have to end up with a constant answer. Our answer can't have any more x's, y's, z's, whatever's in it, right? So the last integral we do will always have constant bounds. And just by using a u substitution on this one, we can find an antiderivative to be negative 1/6 times 1 minus x cubed, evaluated from x equals 0 to x equals 1, and that recovers this value of 1/6. And since this was advertised to us in the activity as the volume underneath the graph of 1 minus x minus y lying above this triangular region in the xy plane, that is exactly the volume of this tetrahedron that is made by these three unit vectors. And it agrees with the value that we got by using the 1/6 of the scalar triple product formulation as well. So there is some justice in the universe after all.